Okay, so this is part 2 of section 5.1, and in this video we're going to talk about free damped motion, right? So by damped we mean motion that is, well, damped, right? So your spring, so you still have, let's say this is the ceiling here. You're hanging a spring and then some mass or a weight on the spring, right? So in the last video we saw that the motion of the weight just goes back and forth in a sine or cosine fashion like this, right? And you know that's going to be true for a while. But if you do this in practice, what happens? Like after some time, this is going to come to a stop, right? So you might go back and forth for a while, but eventually it's going to kind of slow down and get smaller and smaller, or the amplitude gets smaller and smaller until it actually just comes to a complete stop, right? So yeah, as a practical matter, this doesn't go on forever. This periodic motion. Eventually it comes to a grinding halt. I mean, it might take some time to do that, but eventually that's what happens. And the reason is because this weight is moving through air, and air is a medium that provides some sort of drag on the weight over, at least over time. Right. So air is not a very viscous medium by any stretch. But it does provide some damping force, right? And generally speaking, the force of the damping, right, is going to be proportional to the velocity. In other words, how fast it's moving, right? So it's going to be some constant. We're going to use beta for that constant times the velocity. But remember, the velocity is also the derivative of the displacement, right? The displacement from equilibrium. Right, so that's our x. Okay, so yeah, right. So with that, now we have damped motion. It's still free motion because we don't have a force that's driving this motion back and forth. In other words, we pull it and then let it go, or we push it and then let it go, right? So in other words, we're going to get equal 0 here. So these are still going to be homogeneous equations, right? So yeah, what you get is this differential equation here. Well, and if you divide both sides by m, or I think in this, yes, if you divide both sides by m, you get this equation. And let me copy it down because this is the one we're going to be working with for a while. X double prime plus 2 lambda x prime plus omega squared is equal to 0. Okay, so in this case, this lambda here is just beta divided by 2m, so that explains the 2. And then omega squared is just the usual k over m. Okay, as before. Okay, so this is going to be the equation we want to solve for x, right? In other words, we want the displacement. X is a function of time, t, right? And yeah, we do this just the usual way. We're going to get the corresponding auxiliary or characteristic equation. And remember, instead of using m, because we don't want to confuse m and mass, so I'm going to use r here. So this will be r squared plus 2 lambda r plus omega squared equals 0. And so this is a quadratic equation in R. And if you solve that, you get R is equal to opposite of B plus or minus the square root of, that's a square root of B squared. So that's going to be 4 times lambda squared minus 4 times A, which is 1, times C, which is omega squared, divided by 2 times A, which is 2. You simplify all that, and you just get negative lambda plus or minus the square root of lambda squared minus omega squared, right? So we get two solutions, right? R1 is negative lambda plus the square root of lambda squared minus omega squared. And the other solution, R2, is negative lambda minus the square root of lambda squared minus omega squared. Okay, so that's just to summarize all that, that's what we get here for the two solutions. Okay, now what type of solution, in other words, what type of motion you get, right, for x of t depends on what's under the square root, right? The lambda squared, this thing here, lambda squared minus omega squared, right? Whether that's positive, negative, or 0, you get three different types of solutions, right? So this is the discriminant, and we're going to take the three cases separately here, right? So in the first case, in case 1, where lambda squared, oops, I'm going to try to squeeze that in here. In case 1, where we get lambda squared minus omega squared is greater than 0, right? Or lambda squared is just bigger than omega squared. We get a situation where the system is what's called overdamped, right? And it has this solution here. I know these are pretty tiny, but I hope you can read this. So basically, right, there's no sines or cosines anymore, which is maybe a little surprising. We're dominated here by exponential terms, right? So this this e to the negative lambda t here is what dominates, right? And it's multiplied by more exponential terms as well. So what happens here, if I can just sort of squeeze that in here, is that the displacement quickly dwindles off to 0. So if you have an initial displacement, right, it just kind of tapers off to 0. Or if you have an initial velocity, right, if you say pull it downward, it'll pull down, it'll initially go down, but then it'll sort of snap right back up and then quickly dwindle to 0, right? So there's no oscillatory motion, there's no back and forth periodic motion at all here, right? So that's what happens when you're overdamped, right? Imagine putting this weight here, this mass, and the spring system, and just dumping it in a barrel of molasses, right? Some very thick, viscous fluid or viscous medium, right? If you do that, this mass is not going to go back and forth, right? If you pull the spring up, the spring will just kind of extend and then taper off until it basically reaches equilibrium, usually fairly quickly. Okay. So yes, when lambda is big, right, lambda represents, right, how viscous the medium is. It's, right, so the bigger the beta, the bigger the lambda, the more viscous or more thick the medium is, right? Okay. Remember, omega has to do with the stiffness of the spring, right? So if the spring is not very stiff, then this just has back and forth motion. And if lambda is much bigger than the omega, which is what we have in the first case, for the overdamped case, right, then we expect the spring not to do much at all, just kind of to snap back, and the mass will get back to equilibrium fairly quickly. Okay, so that's the first case, right? Case 2, which maybe I'll do that right here. It's actually very similar to this case. It's what happens when you get lambda squared minus omega squared equaling 0, or essentially lambda is equal to omega, or plus or minus omega, right? So in this situation, this is called critically damped. And this is sort of like the edge between overdamped and underdamped, right? This is sort of sort of the edge between those two. Sort of like, right in the middle here. But what happens is not that much different than the overdamped case, right? In the overdamped case, remember, it just quickly kind of snapped back to equilibrium. And in this case here, well, suppose you pull it down, or you pull it down, right? You might end up going back, but then it'll quickly taper off to 0 again, right? Or let's say you just release it, right? If you release it, it might bounce once and then quickly get back to equilibrium. So there might be just this one little bounce, but aside from that, it's very similar to the overdamped situation. Okay, so you can see again, there's no sines or cosines in the motion here for x of t. So the displacement doesn't oscillate back and forth. Again, the dominating term here is the exponential, which means it behaves exponentially and it quickly dwindles to zero. Right? Or in this case, to the equilibrium position, which remember we're calling that zero. Okay, one last case, and that's the most interesting case. Case 3 is when your lambda squared minus omega squared is negative. In other words, the lambda squared is less than omega squared. So in this situation, the lambda is very small, so that might represent a very thin viscous medium, very thinly, right, not very thick at all, like air, right? So this might be a case where you have a spring in air, right? And the idea is that, right, it will go back and forth in a sine or cosine function, in a sine or cosine manner. And you can see from the equations, here are the equations right here, you do get a cosine or a sine and cosine term, or factor here. You still have the exponential term, but because lambda is very small, it's not very effective, right? It doesn't dominate like the sine or cosine does, right? And so this is exactly what we have up here, and maybe I'll show you what happens again, right? So in this situation here, your mass, if you pull it, or push it in this case, and then release it, it'll go back and forth as a sine or cosine function. But over time, that will dwindle, and eventually it'll settle down and reach equilibrium. So the exponential part here is sort of the maximum displacement sort of gets exponentially depressed, if you will, and eventually the sine or cosine, the maximum displacement will decrease, right? So the exponential term will matter, but only over a significant amount of time. Okay, so that's case 3. That's when you have an underdamped situation, right? The damping is not enough to overcome what the spring naturally wants to do, which is just go back and forth in this oscillatory periodic manner. Well, I shouldn't call it periodic, right? It does oscillate, but in this case, right, there's no period, right? We don't use the term period here. You can call it a quasi-period for this quantity here. And likewise, we don't also use the word amplitude. I much prefer the term maximum displacement because the amplitude is supposed to be a constant, right? That's what happens here. Oops, excuse me. Here, when the amplitude is constant, right, that's the maximum displacement. If that changes over time, we don't call it amplitude anymore. You can say quasi-amplitude or damped amplitude, but I'll just use the term maximum displacement from equilibrium. So I hope that helps illustrate the 3 different scenarios here, the 3 different cases you get for free damped motion. Okay, so we can go on to our next example. So this is still section 5.1, but this is going to be an example for free damped motion, right? So this is number 30 from the textbook. And so the question is, you have a 10-pound weight attached to a 5-foot spring, and the spring measures 7 feet in length. The mass is then removed and then replaced with an 8-pound weight. And at that point, then the system is placed in a medium that offers a damping force numerically equal to the instantaneous velocity. Okay, so what does that mean, right? Remember, the force of the damping is proportional to beta times the velocity, v, right? Or I should say x prime, rather, right? So here the force is numerically equal to the velocity, so that tells me that beta is just 1, right? So beta is just 1. Right, so the first question is to find the equation of motion, right? So by equation of motion, you remember what that means. That's just finding, well, first the differential equation and then solving it for the displacement, right? So x of t describes the motion, the subsequent motion, right, after your initial conditions here. Okay, so find the equation of motion if the mass is pulled from a position 1/2 foot below equilibrium with a downward velocity of 1 foot per second. So those are the initial conditions, right? Those are the initial conditions, right? So for part A here, the initial position is 1/2 of a foot. So 1/2 for x of 0 when t is 0. And because it's pulled, right, that means it's hanging from the ceiling and we're pulling it downward. So remember, downward is a positive number, so this will be positive 1/2, right? And then the initial velocity, x prime of 0, well, that's going to be 1 foot per second, right? And because we're pulling it, right, we're pulling it downward, that's going to be a positive velocity, positive initial velocity. Okay, so I hope that's clear. I know this is an awful picture here, but here's the mass, and this is illustrating we're pulling it downward. Right. So this is going to start below equilibrium position, 1/2 foot below equilibrium position, and then we're going to pull it further to give it an initial velocity of 1 foot per second. Okay, so that's the setup here. Okay, so what's next? Well, right, in order to find the equation of motion, we need the equation that expresses the derivatives here. And if you remember, originally we had mx double prime plus beta x prime plus k times x equals 0. And 0 indicates that this is free motion, right? We don't have an external force other than the spring and gravity and the viscous medium. Right, we're not applying an external force, right? So this is still free motion, but it is damped though, right? Because we do have a beta that's non-zero. Right, and you divide by m, and you get x double prime plus 2 lambda x prime plus omega squared times x, right, equals 0, right? And remember, we already solved this, so we already know the solutions. We just have to determine which of the 3 cases we have here, whether this is overdamped, underdamped, or critically damped, right? Okay, so how do we do that? Right. Well, all right, so maybe we should write down the auxiliary equation here. The auxiliary equation will be r squared plus 2 lambda r plus omega squared equals 0. And maybe this is a good time to figure out what is this omega and what is lambda here. So let's start with lambda. Remember, lambda was just beta over 2m. Let's see. Yeah, beta over 2m. So beta over 2m. And we know beta is 1, right? That's from the force is numerically equal to the instantaneous velocity. And what's m? Well, it's be careful. It's not 10 pounds. It's actually 8 pounds. But that's still not the mass. That's the weight, right? So the weight is 8 pounds, and g is 32 feet per second squared, so that tells me that m is actually 8 over 32, or 1/4, right, 0.25 slugs. So 1/4 of a slug. Okay, so 2 times 1/4, 2 over 4 would be 1/2, so 1 over 1/2 is 2. So lambda is 2. Lambda is 2. So now we can write this as r squared plus 4r plus, and what about omega squared? Okay, So for omega squared, we're going to go back to the first statement here, which says we have a 10-pound weight. So we're going to use Hooke's law in this case. 10-pound weight is equal to k times the displacement. Right, so what's the displacement? Well, be careful. It's not 5 feet. Right, so the spring will measure 7 feet after the 10 pounds is attached. So the displacement from 5 to 7 is only 2 feet. Right, so that's the displacement from equilibrium. If 5 feet is the equilibrium, and then it stretches 7 feet, it stretches 2 feet, you get to 7 feet, right? Okay, so that means k is equal to 10 over 2, which is 5. Okay, so, all right, so we know k is 5. What's omega? Omega is the square root of k over m, right? So this is 5 divided by 1/4, which is, wait, is that right? So yeah, k is 5. And m is 1/4. So I guess that's the square root of 20? Yeah, square root of 20 for omega, right? So omega squared is just 20. Okay. All right. So, yep. So omega squared is 20, and we're solving this quadratic equation. All right. So I'll spare you the details. You just use the quadratic formula. You get 2 plus or minus 4i. Right. And so remember, that means your x as a function of t is going to be, right, e to the power 2 plus or minus 4i times t. And we usually split those up as e to the 2t times e to the 4it. But the e to the 4it just gets resolved into sines and cosines. So you get e to the 2t times, let's say, c1 cosine of 4t plus c2 sine of 4t. So that's x of t. Sorry, not lambda, x. Okay. So this should describe the motion. Right, so that answers the first question. Find the equation of motion, and we have that. Although we don't have C1 and C2. All right, so that's a problem. How do we find C1 and C2? Well, we have to use the initial conditions. We haven't used those yet, which are way up here. Okay. So let's apply these initial conditions to this, and we should be able to solve for C1 and C2. So I'm going to do that over here. I hope I'm not writing too small. If I am, let me know. So x of 0 is just going to be e to the 0, which is 1, times c1 times cosine of 0, which is 1, plus c2 times sine of 0, which is 0. So this is just c1, and x of 0 was 1/2. So that tells me right away that c1 is 1/2, right? So that gives c1. Now to get c2, I think we're going to need x prime of 0. Before we get x prime of 0, we might want to just take the derivative of this, and that's going to be a product rule. Okay, so let's see what we get here. So this is going to be, let's see, first times the derivative of the second. So e to the 2t times the derivative of this will be negative 4c1, although c1 is 1/2, so 4 over 2 is 2, so negative 2 times the sine of 4t plus c2 times 4 cosine 4t. So I think that's a plus 4c2 cosine of 4t. All right. So first times the derivative of the second plus second times the derivative of the first. So the derivative of the first will just be 2 e to the 2t, and then times the second, which is c1, 1/2 cosine of 4t plus c2 sine of 4t. So sorry I ran out of space. I had to write it on 2 separate lines. And I'm tempted to factor out the e to the 2t, but I think in this case we don't really need to. We just need to plug in 0 here wherever we see a t. And so e to the 2t is just e to the 0, which is 1. So what do we get? We get negative 2 times 0 plus 4 times c2 times cosine of 0, which is 1. Plus, so now we have 2 times 1 times 1/2, which is 1, times the cosine of 0, which is 1. So I think that's just 1, and then sine of 0 is 0. So 4 times c2 plus 1, what is x prime of 0? It's just 1. Right? So that tells me that c2 is 0? Hang on. I'm not sure that's right. So let me see if I did the derivative correctly here. So first times the derivative of the second, so that's this. Derivative, I think that's right. That's right. Plus second times the derivative of the first. So I think that's right. The 2 cancels with the 1/2. I think this is right. Okay. All right. Well, so let's go with that. I don't know. Something's wrong. Something's wrong here. So I guess I'm going to have to go back and see what I did here. E to the 2t. Okay. All right. I think I got it. Negative b, right? B is 4 here. Yep, there we go. Negative 2 plus or minus 4i. Okay, that makes all the difference in the world. That's negative. Hang on. This is negative e to the negative 2t. E to the negative 2t. Yep. All right, well, so that makes, I think that makes this negative here. So let me see if I can erase this and make this a negative 2. So this becomes a minus 1. Yep, so I have to erase this as well. And yep, C2, 4 times C2 equals 2, so C2 is going to be 1/2. Okay. Yeah, what a difference a sign makes, right? This should be negative 2, not positive 2. Okay, well, I'm glad I figured that out, I guess. Better late than never. Again, I apologize about that. This is, this is not easy to do in real time here. All right, so C2 is 1/2, C1 is 1/2. So now I can finally write down the equation of motion. In other words, the displacement as a function of time. So this is going to be e to the negative 2t times 1/2 cosine of 4t plus 1/2 sine of 4t. Okay, there we go. Phew. All right, well, that's part A. Right, so that's the equation of motion. That tells us the motion of the spring. Okay, so which of the three cases do we have? Well, because we have the sine and cosine here, this is going to be an underdamped system. So this is underdamped, case 3. Underdamped. All right. All right. Well, now I think we can move on to part B. Part B is express the equation of motion in the form with a phase angle. So let me scroll back up here so I remember. Yep, we want this form right here for the phase angle. So in other words, we want to find this phi here. This phi here. So, yep, so in other words, we want to write this equation down here in the form of A times, let's see, oh, how soon I forget. Is it cosine or, yeah, we need the e to the negative 2t here first. Oops. E to the negative 2t times the cosine of, I think it was t times the square root of lambda squared minus omega squared minus phi. And silly me, we already calculated this lambda squared minus omega squared. Remember, lambda is 2, so lambda squared is 4. And then omega, did we ever find omega? I don't think we found omega. Oh yes, square root of 20. So this is 4 minus 20, which is negative 16. And then the square root of negative 16 is the 4. So that's the 4 we got here, right? All right, so this is going to be a e to the negative 2t times the cosine of 4t minus phi. Right? So this is the form we want. Now we just have to find phi. And we can also find a, of course. Again, a not really an amplitude here, but it's you know it's the damped amplitude. So yeah. So let's do that quickly, even though they don't ask for that. So this is part B right here. So a, of course, is just the square root of c1 squared plus c2 squared. So 1/2 squared plus 1/2 squared is 1/2. So this is just the square root of 1/2, or if you prefer, square root of 2 over 2. All right, now the question they ask for is the phase angle. So that's phi. And if you remember, phi is the arctangent of c2 over c1. And, well, c2 equals c1, so 1/2 divided by 1/2 is just 1. So this is just the arctangent of 1. And I think I remember that. I think that's just 45 degrees, right? Pi over 4. So that's my phi. And now, I can scroll down a little bit here. We can rewrite this x of t in this form here. Right, so this is for part B. This is part A, part B. So a, which was square root of 2 over 2, times e to the negative 2t times the cosine of 4t minus pi over 4. And so that writes the equation in the form with the phase angle. So I hope that helps. And I'm looking, let's see, I'm looking at the answer, and that's not what the book, oh, yes. So the book has the following answer. Let me just write it down. So the book has this answer, right? 1 over square root of 2, which of course is the same as square root of 2 over 2, times e to the negative 2t times the sine of 4t plus pi over 4. And so this is perfectly correct as well. This is the book's answer. This is my answer. So you notice that you get a different phi here as positive pi over 4, or I'm sorry, well, no, this was a minus, right? So here, I think it's the same phi in both, but in this form it's a plus instead of a minus. So you're off by, pi over 2 here. Like I say, either way is correct. And you should convince yourself that this is the same as this, right? You're just using the, transforming you're doing a phase shift. You're just doing a phase shift here. That's all. Okay. So, so this is perfectly fine too. It just depends on whether you want to express it in terms of cosine and sine. So I prefer to write this in terms of cosine instead of sine, but I think the book has the opposite approach and writes it in terms of sine. Okay. Well, we have one more question to answer here. Part C, find the times at which the mass passes through equilibrium heading downward. Okay. So passing through equilibrium here, so this will be part C. Part C. Equilibrium, of course, just means x is 0. So we're just solving this equation when x of t equals 0, right? And you can use any version of these for x. Actually, it might be more helpful to use this version for sine here. So here, we want to solve, hang on. Okay, so we want to solve this equation here, square root of 2 over 2 times e to the negative 2t times the sine of 4t plus pi over 4 equals 0. So we can divide by square root of 2 over 2, and we can divide by this e to the negative 2t. We can divide by this whole thing because it's not equal to 0, right? This is never 0. And so we really just have to solve this equation. And you remember that, right? Sine of theta equals 0 means that theta is just some multiple of pi. Okay. So in this case, our theta is this 4t plus pi over 4. Yep. So 4 times t plus, that's a t, plus pi over 4 is just n, some integer multiple of pi. So solving for t, we have 4 times t is going to be, so let's see, this is n pi minus pi over 4. I'm tempted to just get a common denominator here. So this is going to be, let's see, pi times 4n minus 1 all over 4. And when you divide by 4, you get that t is equal to pi times 4n minus 1 all divided by 16. Right? So n, and these are just integers, right? N can be any integer here. Although we might as well start at, I don't know, n is equal to 1. Right? So I guess these are the times. And I just realized that that's not going to be quite true here. We're not quite done with this. Shoot. So here's the reason. Remember the original question, which is way up here now. Find the times at which the mass passes through equilibrium, right, heading downward. So maybe we should draw a little graph here. Right. So originally, I think we started down here, right? We started down and it's heading downward, so it's going to do this and then pop back up and then back down, up, down, like that, in that format. So our first n here means it's going upward, not downward. Right? So remember, down is positive, up is negative. So we have to skip the first one and then go on to the second one where it's downward. In other words, we want it through equilibrium but heading downward like this. So we want this one, this one, this one, this one, and so on, right? So let's see, how can we take care of that? Well, maybe I should write out, yeah, let's write out some of these terms here, right? So we don't want t to be negative. So if n is 1, this is going to be 3 pi over 16. Right? So I think that's the first one here. This is 3 pi over 16 here. But we want to skip that, right? So we want to go on to n is equal to 2. So that's 8 minus 1 is 7, 7 pi over 16. So that's this one right here, 7 pi over 16. All right, and then skip when n is 3, 12 minus 1, 11 pi over 16. And then when n is 4, we get 15 pi over 16, and so on. Okay, so we want, again, the ones where they're heading downward, or the second one, the fourth one, and so on. I think I crossed the 1 there. So this one and this one, right? Okay. So, yes. And so you're just adding 8 pi over 16 to each of these. So the next one will be 15 plus 8 is 23 pi over 16, and so on. So let's see, how can we express that? So we'll start with 7, right? And then we add 8 pi to that. 8 pi to that. I'm sorry, 8n, 8 times an integer, right? All times pi over 16. So this is 7 plus 8n over 16 all times pi. So these are the times at which it's passing through equilibrium heading downward. Okay, starting at n is equal to 0, I guess. Oops, okay, so n is 0, 1, 2, 3, ... All right, so I think that answers part C. Find the times at which the mass passes through equilibrium but heading downward, right? If they wanted the times passing through equilibrium, heading upward or downward, then that would have been a lot easier. That would have been these solutions right here. We could have just left it at that and say started at n equals 1, 2, 3, and so on. But since they wanted downward, we had to skip every other one of these solutions here. And when you skip the first, the third, the fifth, and so on, you get these. So I hope that helps. So that's a fairly standard problem in this section. Yes, it involves a lot of algebra here, and I hope that isn't too confusing. So yes, and apologies for missing the minus sign here. That's a problem. Well, it's a problem, but eventually I fixed it, and so I think this is correct. At least the book agrees with me that this is the correct solution for part A. And this is my part B. This is the book's part B. And yes, it's a little easier to solve where sine is 0 than cosine is 0. But we would have gotten the same thing if we set this equal to 0 and solved for t here. It just would have been a little more of a hassle because you're talking pi over 2, 3 pi over 2, and so on. All right, so that's that.